Okay, so we just covered axial compression and tension, and now we're going to talk about shear. Shear, and I have the chopstick again. Shear is basically if I were to put my fingers together and push one finger down this way and the other finger up this way, then inside the beam here, we would be experiencing shear. And it's the tendency for things to like rip. So paper is the easiest thing to shear, and it's also wood. So if I push up and pull down at the same time, that's shear failure. And it's different from, maybe axial tension on paper is actually pretty good. Compression, it just buckles. So tension is pretty strong on paper, but shear is not. So there are different types of loading situations that result in more or less stress, and we're about to get in. So here they offer, maybe a larger block or beam, and they have maybe an outcropping, and you're trying to take the outcropping and push it on and it's all one material. So this is all just one piece, and you're just pushing the top. And shear stress is this little T with a squiggly on top. I don't know the Greek name for this symbol. I don't use shear a lot in my engineering. And they're specifically saying average, not at a point, but across the entire plane. And P is force, of course, area. So force over area. So it's still stress. And so, of course, you're going to have, KSI and megapascals still. So shear happens a lot. Here's an example of 2 sheets of steel with a rivet or a bolt. So anytime you have like a lap, here my 2 hands are forming a lap, and then they're trying to pull apart or whatever, so you're going to join them with a rivet. Now that rivet is experiencing shear around its cross section here. So the area is the rivet where you would cut it. And the force, I guess they're just showing that it's distributed load on that beam. And they're going in different directions. Yep. Press Alt. Here they have a more complicated 2 rivets, and those rivets are each absorbing okay, so it's 3 pieces of steel. There's 4, so 2 pieces are coming up, and then on top and bottom there's a sandwich, and then 2 rivets through that. And so it's just kind of breaking it down a little. Everything's a little different depending. If you have a keyway on a shaft, which is very common in automotive, then the key is being sheared by the rotation of the shaft. Or it's trying to be. And so in that instance, the area is basically where the key, so let's see, you have like a gear. There's a shaft. And on the outside of that, you have a gear with a also keyway in it. So there's like a gear around here. So now you're gonna stick a Woodrow key in there, and so that keyway is responsible for holding the maybe the crankshaft and the part of the timing. So they can't separate. They can't rotate. So for this not to fail, this cross section right there needs to be thick enough. So if you sketch this Woodrow key, so like that. So he's basically being sheared this way and that way. So it's only a rectangle, and the top and the bottom have different directions of load. What else we got? Oh, so just like any other stress problem, you could calculate the required area based on the ultimate stress. So you could target the stress. That's what this is saying up here. How is this in shear? Bearing stress? Bearing stress is not shear. This is normal stress. Okay.